Welcome to an overview of mass spectrometry, a technique that turns ions into actionable insights. This slide shows the full workflow from ion generation through mass separation to spectral patterns and data analysis, illustrating how raw particles become identifiable peaks and finally interpreted results. Think of it as a pipeline that converts chemical signatures into information you can use for identification, quantification, and discovery. Here we compare common mass analyzers and why the choice matters for performance. Different devices like quadrupoles, time of flight, ion traps, orbitraps, and FTICR trade off mass accuracy, resolution, speed, and dynamic range. So the right analyzer depends on whether you prioritize fast scanning, ultra-high resolution, or the broadest dynamic range. Choosing wisely dictates detection limits, spectral clarity, and overall sensitivity for your application. Ion detection systems translate ion impacts into measurable signals, and each approach has pros and cons. Electron multipliers give high sensitivity at low currents. Faraday cups offer precise direct charge measurement with excellent linearity, and image current detection is non-destructive with high accuracy. All these raw signals then go through signal processing and calibration to produce the final mass spectrum you interpret. This page outlines a standard spectrum and a consistent data processing routine to get reliable results. We subtract baseline to isolate true peaks, evaluate noise to establish signal-to-noise thresholds, assign monoisotopic peaks for accurate mass calculation, and determine charge states from isotope spacing. These steps remove artifacts, improve confidence in peak picking, and prepare spectra for downstream identification and quantitation. Isotope pattern analysis explains the origin and use of M+1 and M+2 peaks, which arise from natural isotopes like 13C, 34S, 37Cl, and 81Br. By comparing measured isotope envelopes to theoretical models, you can confirm or reject candidate formulas without always needing ultra-high resolution hardware. This spectral matching speeds up elemental composition determination and helps narrow plausible molecular formulas for further analysis. Fragmentation mechanisms reveal how molecular ions break and how that informs structure elucidation. Primary pathways include alpha cleavage and McLafferty rearrangements, while inductive and charge site cleavages are additional routes driven by bonding and ionization. Mapping dominant fragments, identifying neutral losses, and validating proposed structures with tandem MS and integrated data lets you reconstruct and confirm molecular architectures with confidence. Tandem, MS, and activation modes enable targeted interrogation of ions using different fragmentation chemistries. CID and HCD induce collision-based dissociation for predictable fragments. ETD transfers electrons, preserving labile modifications. And IRMPD uses infrared photons to drive dissociation, each offering unique selectivity. Scan types, like product ion, precursor ion, and neutral loss scans further tailor experiments to separate isobars, map label modifications, and improve targeted analysis. Analytical fundamentals cover resolving power, mass accuracy, and calibration, key to distinguishing closely spaced masses. Resolving power, defined as R equals M over delta M, determines whether nearby peaks are separable. Mass accuracy, expressed in ppm, quantifies measurement error and improves with internal standard calibration. Together, these parameters reduce candidate formulas and enable precise composition calculations, making confident identifications possible in complex mixtures. Coupling mass spectrometry with orthogonal separations adds dimensions that help deconvolute complex samples. GCMS separates volatile compounds by retention time. LCMS handles non-volatile or polar analytes. CEMS separates charged species by migration, and ion mobility adds drift time to distinguish isomers by size and shape. Combining these dimensions increases peak capacity, improves confidence in identification, and enhances analysis of biological and environmental samples. Bottom-up proteomics workflows take proteins to peptides and then to quantitative insights. Enzymatic digestion creates peptides that are optionally labeled with isobaric tags or analyzed label-free, followed by LC-MS acquisition and database searching with FDR control. This pipeline enables deep proteome coverage and differential expression analysis, with label-free offering broader dynamic range and isobaric tagging providing multiplexed, higher precision quantitation across samples. This slide contrasts untargeted discovery with targeted MRM quantification. Untargeted feature detection profiles global metabolites using accurate mass, retention time, and MS-MS matching to reveal novel biomarkers and unknowns, while targeted MRM focuses on specific known compounds for highly sensitive, precise measurement. The two approaches complement each other. Discovery defines candidates and pathways, and targeted assays validate and quantify them for clinical or environmental applications. Mass spectrometry in hospitals supports routine clinical workflows across many applications. Examples include newborn screening for metabolic disorders, rapid vitamin D assays, therapeutic drug monitoring for dosing guidance, and MALDI-TOF pathogen identification for fast microbiology results. These implementations emphasize speed, specificity, and integration with lab systems, ultimately enhancing clinical decision-making by delivering accurate, actionable data to clinicians in a timely manner.